In this video, we want to discuss the basics of system model simulation. It's actually execution of system model and analysis on top of that. So we want to discuss what matters and what is important when you execute your system model in SysML to test behavior interfaces, performance characteristics, and do analysis on top of that. So we'll discuss like the most common structure you would model to execute and the main rules to do it. So first of all, we'll create a model. As you see, I'm using just generic SysML project. You can use UML, you can use UAF, and until it runs on top of UML, it will execute. And I will start with block diagram. So here we have like a couple of blocks. Those give us structure, right? So it will be, for example, satellite, then will be payload, and then will be infrared scanner. Here we have the structure. So if you'll execute that simulation run, you see we have all that structure as runtime instance. So we have that all information. You see parts, right? Because we executed that block, we have the structure. Here we have console. So all the step-by-step execution information will be here based on the severity level selected. And here is the session. So all the sessions which are running in parallel. So here we see that we executed block. So block session is running. So now if we'll add some properties, like for example here, I want to add value property like power. And that could be like in watts if I will load, the ISO library, which is really working as a real properties by default, real type of properties. All those ISO properties, you can create your custom properties types, but just in general to use one of the available ones. So I can put the beginning of the search. Here you go. And now so this property you can even assign the value here, like for example 20. You see the unit is here. So if I will execute, as you see, I can now monitor that value, change it runtime, right? 42. Even I can create requirement which will constrain that property, because we have text-based analysis of requirements. So power limit, I can say that power consumption by shall be less than 30 watt, right? And then say that it satisfies, right? So this will constrain, and if I will switch this mode on, project general user requirements term glossary. Okay, so now I have this, you see, constraint power equal shall be less than. So move mouse over and see power less than 30, right? So if I will run this analysis simulation run, you see now I have this green, and requirement power consumption by air scanner requirement is satisfied, requirement 1. If I will put something like 31, it's already not satisfied, right? So now structure works, right? And there could be like, for example, like a communication device here, right? Communication and other things. Structure works in the simulation. You see this is the instance, random instance of that structure. We can manipulate during the execution properties, but also those properties can be manipulated automatically. And who would manipulate them? The behavior, right? So in most cases, behavior would be like, first of all, state machine. In the more complex or blocks which behavior we want to model, we can model them in the state machine. And then also the functions are very common to model in activities. Why to use state machines? First of all, because state machines allows us to easily switch on and off states of the block, at the same time start functions of that system. So let's say IR scanner, I right click, create diagram, and that would be state machine diagram. And as you can see here, this diagram becomes available inside of the scanner. And very important, if you select the block, go to properties, expert properties, you see that this classify behavior. So when you execute the structure, if I will simulate the structure, the only behavior which starts running is the classifier behavior. And you see when I initiate simulation, I see the structure. Now if I will click here play button, actually behavior starts, right? So each block can have only one classifier behavior. That behavior starts automatically. It has access to all the properties of the block as a context of that behavior, and also it can call other behaviors, and those other behaviors would become called as from that same context as they were executed. So they could exist somewhere else, you know, like be independent, but executed from that single place. So okay, I will go here. It will be off, could be like uppercase. Then stand by, and then on, and then go. So power on, that creates the signal automatically. You see that I got the signal, and that I could, you know, use by drag and drop here on transition. Okay, and I can just start typing power and click control space as auto completion. You see on is available, but power off is not available. So I have those signals. And then here after 5 seconds, this is time event, which gets introduced. And you see here we have time event automatically. 5 seconds is relative, right? Automatically it parsed that what we typed in here is the signal event power on, right? Now I want to control this off or standby and on power, so I can actually put here on entry, choose the opaque behavior, and here I can just type the property name and adjust the power. So power equal 0, just by name. On standby I can do like entry opaque behavior will be power equal 2, and here on again I can do big behavior power equal 20. Okay, so now when we execute that model here run, and actually you see I can run in context behavior. Any behavior can be executed just as a behavior like that, or in the context, run in the context. So then the block of that behavior gets executed. But I want actually to execute the whole system, so I can run satellite. And you see now I have full picture. Plus I can run behavior, execute behavior. Here is off. We do the power on. So the power gets updated to 2. After 5 seconds, it will switch to the 20, and then on power off, I will get the off state, and I can monitor that in the state machine. So I can go chart. So I can go here to the IR scanner, show in the timely chart state, yes. And I can see those states, IR scanner states, and then send the signals on. Then after 5 seconds it switches, and here is now in on state and can switch to off state, then switches to off state, and I see what signals were triggering that. Okay. So as you can see here, and we can actually monitor if the property gets out of the bounds. We'll also see that if we are tracking the value property here in this chart. In this simulation, we can do time series chart of the value property here, you see, and run the behavior 0, right? And then send signal. Power on. You see it's now 2, and in 5 seconds we'll get 20. As you can see, the default time is milliseconds. So it's not very convenient for us because we want that it would be in seconds. We have no smallest granularity of time as 2 seconds here actually. I just wanted to show that if we increase the time here, we can see that also requirement failed here. See? We can actually control that through simulation config. So how to control through simulation config? It can create simulation configuration in the simulation configuration diagram here, and then run config. Here will be like time-based simulation. And then here we will choose satellite as a, you see I'm dragging on the header as an execution target, and then I will go here to the time properties and will say start time 0, step delay 1, step size 1, and time unit seconds. That will make that single step size as a 1 second and delay of 1 second by 1 unit, so 1 second by 1 second. So that will be actual real-time 1 second simulation as a 1 second. If we'll do like 0.5, it will be twice faster. If we'll do 2, it will be twice slower. So 1 second, and that's it for us. That's enough to run those simulations. And now you see simulation config is on the top. I can execute that. I get that structure executed, and then I can start tracking the power. Actually, we can even automate that power tracking, so we can create a time series chart here, call it power, and then drag the payload on the chart, and then choose the value, as the only value we have is the power, and then take that power and drag it on that to see it as UI, right? You can have multiple UIs from here, you know, select that one of that time series chart, and then we drag it, and you see now I see that iris scanner, because we selected payload as a, so we will modify this refresh rate, so it will be 0, and linear interpolation, it's not suitable for us, let's put it false. And that's it, you know. So once we will run the simulation, you see that it jumped to 20 because initial value was 20. And now if we will track the time here, so we will go power on. You see the time is in real time with 0, if we 1 delay by second, 1 second delay, and here we see that it jumped on the 5th second to 20. And now if we'll switch off, you know, it switched to the 0 because there was no delay on that, right? So now we'll here, we are here. Then we can put it back to this standby. Again, it's ticking, and then it again jumps. And we can decrease that delay here by going to the time properties and saying, like, for example, 0.2. This will speed up things a lot, you know, and we can run the simulation again. And then here, switch to this one. Still, we see the 5 seconds took to execute, but it executed much faster. Those 5 seconds, 5 times faster. And that's the goal, actually, to have the discrete time, right? And to have the discrete simulation, which would not require, you know, waiting for that to execute in real time, but get actual results. Now, what we can do else, you know, we can actually execute the activities which would run, you know, and modify those properties. Those activities can be executed directly by the state machine. So let's do it, right? Like, let's say, do the monitoring. Let's do the activity. That activity can be created anywhere, right? Right click, create diagram, SysML activity diagram. Start like this, monitor, then let's do like this. Let's use opaque behavior. Opaque action can actually read the properties. It has the same body and language, which can be executed in any body and language. We can by default use English. It takes then the standard script from the options in the project, and we can just say like that, power x equal power. So it will read this power property, right, and assign to x, and we can actually type the name of actions, like read power, or like read power value, and we can choose like simple properties to show, instead of body and language, to show name. You see, constraint mode name, and I think not this one, there would be another one, properties, show body here, display name, show action name here, read power value. So we can choose show body, what it actually does, reads power and assigns to x, or show name. So first of all, maybe we want to show body to do their thing, and then later we want to understand what it does, you know, from the simulation perspective, and then later maybe human friendly show action name. Okay, so this opaque action now assigns to x power, and x is runtime value, so we can just put the output pin like x of type real, because the value of the power is in real type, and then we can push it to the signal, which we will send to the power value signal, which we will send to the power value signal to the external device. New argument pin, like this, and you see the signal got the argument, right? It could be like, for example, power by name I assign to the signal, and that signal could leave us through the some port from IR scanner, and then I could come back here and merge at this level after this. So here we have it like that. And then what we will do, we will assign this activity, take this activity and assign this activity as a do activity here. So until we are in this state, we are running this activity. This activity, as you can see here, is executing, and is executing in circle, and actually can put some delay here and type the delay like 10, let's say 5 seconds. So each 5 seconds I monitor power value and send that power value, and that power value gets sent through the interface. So this will be the port, and see that it's data interface, and let's say that it goes to this communication device. That's called also data. No type is assigned. We kind of can just put the name. That's enough to run simulation. You can also assign type. That would also be another thing. And now to connect those interfaces, we need to create internal block diagrams. So we can create it in top level, satellite level. And then we expand this payload, choose this port, and choose this port, and then connect those ports. Those ports could be connected like this, or we can do modular, create the gate connector. So for example, even like that, we can select connector and go here, delegate ports. And you see it created this delegate port which will work in the same way. So we will notice that once we execute simulation, we'll actually send this to this port, because this port is proxy port, it's transparent, so it will just pass the data to the final port and actual final block. So let's now go to our behavior state machine, go to our activity here, and go to our actual activity of monitoring. I will rename this activity to monitor. And it really reads the power value. It actually could modify it, you know, if we would want. It could say like multiply another property, or like do something like, for example, multiply by 2, just in general, to show that you can do those things like multiply by 2, and then assign to X, and then send it to the port. Which port? The port is actually of the IR scanner. IR scanner, here we have the port, data port. We need that port because this is the port where it leaves this scanner block, right? So this port. Now we can go to this internal block, actually open the state machine here. This is state machine of payload. Also open the activity diagram. Here we see this is that activity diagram, and run the simulation. Here we have the simulation running. And we can actually now send those triggers. So let's select the block to which we will send the triggers, so IR scanner, and then send on. You see, we see that it's on. It passed the value, right? And you see every 5 seconds it passes the value. We don't need to wait longer than we have specified the delay. If we would specify delay 0, it would run the million executions in a few seconds. We don't want that, that's why we specified some delay. It's not real time because we specified deliberately it would be 5 times faster. And see, now it runs the value. I could catch that value here. So let's do it in here. I will specify that I will catch, wait for the value, and then read the value. So here I could create activity diagram. So create a diagram, activity diagram, and then I would put accept event action. This would be event as a signal. So which signal is that? Is power value signal. And then it has, it is important to mark it as in Marshall, that all the outputs of the signal would be treated as separate properties, not as a single one. And then here, if I will click on that, synchronize signal properties by accept event actions, signal accept event actions by signal properties, I see the power here is output, and then I can use the opaque action, say like last power value, and that last power value equal, let's say, Y, and then here I will put the input pin, which will be Y, and this power will come as a Y, and then I get last power value assigned, and this last power value could be the property in communication system, which would be real, let's say. Yeah, I have it assigned as a real. Now it's wrong, so I typed real. I need to choose it from auto completion control space, real, like this. Here we have it. Again, my mistake. Select it, then use real uppercase like this. So now if I will run the simulation and I will track this activity diagram which I just created for the communication device. I have it here. You see it's activated and it waits for the signal. But I'm still lacking the cycle here, right? So I need to have a loop back, merge, right? And then also initial node like this, and then here we'll create the loop back. Okay. So this, right? Okay, and then go back. Here I have this activity diagram. Now if I will trigger my air scanner to on, it will start sending those signals. And you see communication device has now 40,000. If I will update this to something like 30, so this will be 60,000, 60, because it multiplies by 2, right? You see, it's already 60. So that's how we connect activities. That's how we use ports. That's how we send signals. That's how I create state machine in connection with the structure. So first of all, the states are very convenient on any block as a main behavior, classifier behavior. Activities are most convenient to demonstrate the functions like monitor function executed on this on state. We can have other functions executed on other states, also the same one, you know. Here we just skip the states, put the activity, but what we got, we just now have one single function executed in this communication device. What if we use states, we could have multiple functions orchestrated by the state machine, right? Also, here we show that you can actually track requirements verification in the chart, and also use configuration for the simulation time switch, and to switch from the real-time to the model-based clock, and also track automatically properties in series chart or other type of charts, including requirements verification. That's pretty much it. You know, if you want more things like user interface simulation and parametric diagram simulation, there are other videos on MBSE execution channel. Please check them, and we'll expand this basic demo to other levels. Please give your feedback in comments, request what next step to do. Thank you.